The modern agricultural system thrives on scarcity and standardization. Yet hidden in the marginal dirt of almost every continent lies a plant so nutritionally dense, so effortlessly abundant, that it posed an existential threat to the very idea of packaged wellness. This succulent green, capable of delivering measurable quantities of the complex fatty acids typically confined to deep-sea marine life, and overwhelming antioxidant profiles that dwarf standard domesticated citrus, was not conquered by science. It was deliberately erased from the collective plate and reclassified as a nuisance weed because its yield was too uncontrollable and its value too freely distributed. For millennia, it was the emergency ration, the anti-scurvy shield, and the heart medicine of empires, only to be systematically suppressed the moment global commodity markets began demanding profitable uniformity. Welcome to the Lost Archive. If these stories of forgotten scientific leverage and biological resilience matter to you, the most effective way to ensure this wisdom is preserved and resurfaced is simple. Subscribe, hit the notification bell, and share this file widely across your network. The historical anchor point for this narrative reaches back far beyond classical antiquity, though the medical texts of Hippocrates and Pliny the Elder certainly documented its powers extensively. We must travel further back, to the Fertile Crescent of Mesopotamia, nearly 4,000 years ago, where archaeological evidence confirms its systematic cultivation. The technical identity of this resilient botanical anomaly is Portulaca oleracea, commonly known as purslane. Unlike the delicate leafy greens engineered for monoculture, purslane is an annual succulent herb defined by its reddish stems and paddle-shaped leaves, capable of storing water and nutrients with remarkable efficiency. Its global distribution is not accidental. It traveled along ancient trade routes, appreciated by Persian, Egyptian, and later Roman civilizations not merely as a foodstuff, but as a genuine pharmacopoeia for alleviating inflammation, treating wounds, and purging intestinal parasites, solidifying its role as a fundamental staple before the rise of specialized agricultural dependence. This ancient lore suggests a profound knowledge of its phytochemical density, a knowledge that modern science is only now painstakingly reconfirming long after its deliberate removal from industrialized farming cycles. The central conflict leading to purslane's suppression resides precisely in the confluence of two highly specialized biological advantages: its unique lipid profile and its extraordinary photosynthetic mechanism. Concerning the lipid profile, purslane exhibits an extremely high concentration of alpha-linolenic acid, or ALA, which is the essential plant-derived precursor to the crucial long-chain omega-3 fatty acids, eicosapentaenoic acid, EPA, and docosahexaenoic acid, DHA. While ALA is found in various seeds, purslane's leaf tissue contains a remarkably favorable ratio of omega-6 to omega-3 fatty acids, often reported in studies as low as 4:1, and sometimes approaching 1:1, a balance rarely seen outside of wild forage or cold-water fish. This ratio is critically important because the modern Western diet often presents a highly inflammatory ratio, sometimes exceeding 20:1. The key biochemical mechanism here involves the highly conserved pathway requiring delta-6 desaturase enzymes, which are responsible for converting the shorter-chain ALA into the longer, biologically active EPA, and subsequently DHA. Most terrestrial vegetables contain insufficient ALA or are overwhelmed by pro-inflammatory omega-6 excess, making the omega-3 acquisition dependent on highly profitable aquaculture or extraction industries. Purslane, by providing a readily available, terrestrially grown source that dramatically shifts the dietary fatty acid balance toward anti-inflammation, represented an immediate, accessible threat to the emerging dietary supplement and industrial fishing complex of the mid-20th century. Beyond its lipid profile, purslane possesses an agronomic superpower that made it incompatible with standardized, high-input farming. It utilizes a highly efficient C4 photosynthetic pathway, and under specific drought or heat stress conditions, can switch to a form of crassulacean acid metabolism, or CM. Standard crops utilize the C3 pathway, which is highly sensitive to heat stress and inefficiently utilizes carbon dioxide, leading to photorespiration and yield loss when water is scarce. Portulaca oleracea, however, employs specialized leaf anatomy, known as Krantz anatomy, utilizing an extra layer of mesophyll cells to concentrate CO2, maximizing efficiency even in extreme heat. This biological resilience allows purslane to accumulate high concentrations of protective micronutrients, notably ascorbic acid, vitamin C, and alpha-tocopherol, vitamin E, along with significant quantities of non-protein thiols, such as glutathione, a powerful intracellular antioxidant that recycles other antioxidant molecules. The data confirms its vitamin C content often surpasses that of conventionally grown oranges, while its tocopherol levels are among the highest found in any edible leafy green. Its ability to achieve such nutrient density in marginal soils, without the need for sophisticated irrigation or high-level nitrogen fertilization, made it impossible to integrate into a controlled, commoditized food system predicated on patented seeds, proprietary fertilizers, and predictable, but ultimately inferior, yields measured primarily in bulk tonnage rather than nutritional density. The easiest and most economically rational decision for the rising agricultural-industrial complex was not to compete, but to dismiss the plant entirely by assigning it the pejorative label of a ubiquitous, pesky weed. The resilience of purslane, however, transcends market manipulation, manifesting most clearly in moments of systemic crisis where human survival depends on access to uncontrolled, biologically potent resources. During the economic depressions of the early 20th century, and particularly during the prolonged sieges and resource shortages of the Second World War across Europe and parts of Asia, purslane experienced an involuntary but crucial resurgence. When standard supply chains collapsed, and the cultivated gardens were either bombed or stripped bare, people turned instinctively to what survived the worst conditions. Purslane, which can produce seeds that remain viable in the soil for 40 years or more, and which sprouts readily in the cracks of pavements and bomb sites, provided essential caloric intake, along with the micronutrient density necessary to stave off nutritional deficiency diseases like scurvy and pellagra, which historically plague populations relying solely on stored grains during conflict. Its high mucilage content also provided a soothing benefit for digestive complaints rampant during periods of dietary stress, essentially acting as an accessible, self-sowing nutritional lifeboat. The irony is stark. The plant dismissed by post-war agronomy as worthless became the sustaining factor when that same industrialized system failed under external pressure. This biological saga of Portulaca oleracea, the lost garden gold, offers a profound philosophical conclusion regarding human innovation and control. The pursuit of standardized efficiency often leads to an unconscious rejection of deep, localized resilience. By marginalizing purslane, humanity chose uniformity over ubiquity and fragile control over enduring accessibility. The story of its suppression is not unique. It is a recurring pattern where natural abundance and intrinsic value, because they cannot be easily metered, branded, or patented, are deemed incompatible with a profit-driven structure. We are constantly reminded that the most powerful, foundational elements of life, air, water, and incredibly resilient nutrient sources like purslane, are often the things we overlook or discard entirely, precisely because they offer the universal lesson that true survival is not reliant on manufactured scarcity, but on recognizing the inherent, tenacious value lurking just outside the lines we draw. The unparalleled nutritional density achieved by Portulaca oleracea is rooted in an extraordinary metabolic architecture that modern botany is only beginning to fully appreciate, demanding a pivot from the socio-economic narrative of suppression to the rigorous underlying chemistry of its success. Specifically, the designation of purslane as a superlative source of plant-derived omega-3 fatty acids, principally alpha-linolenic acid, YLA, 18:3 and 3, is chemically non-trivial. While standard cultivated leafy greens contain trace amounts, Portulaca oleracea accumulates ALA concentrations ranging typically from 300 to 400 milligrams per 100 grams fresh weight, often representing up to 65% of its total polyunsaturated fatty acid, PUFA, content. This massive sequestration is localized primarily within the chloroplast membranes, specifically in the form of galactolipids such as monogalactosyldeacylglycerol, MGDG, and digactosyl diacylglycerol, DGDG. These lipids are essential for maintaining the fluidity and structural integrity of the thylakoid membranes, especially under the high light intensity and thermal stress inherent in arid environments. This biological imperative, high ELA synthesis as an evolutionary adaptation, provides enhanced membrane stability against photooxidative damage, a sophisticated biochemical design inherently superior to that of omega-3. Poor cultivated crops that evolved under low-stress, high-input agricultural regimes optimized solely for rapid vegetative mass. Furthermore, this extreme drought tolerance and subsequent micronutrient hypertrophy are synergistically linked to purslane's highly adaptive photosynthetic pathway. Unlike the vast majority of domesticated crops that utilize standard C3 photosynthesis, purslane employs a rare, facultative C4, crassylation acid metabolism, CM, intermediate system. This plant can effectively switch its carbon fixation strategy, employing the efficient C4 pathway during conditions of adequate water supply, which spatially separates the carboxylation process to minimize photorespiration, but transitioning to CM under severe water deficit, temporarily separating CO2 uptake via nocturnal fixation. This biochemical flexibility drastically reduces transpirational water loss and ensures maximal water use efficiency, WUE. The resulting metabolic surplus and minimized stress allow the plant to shunt metabolic energy away from simple carbohydrate storage and toward the rapid synthesis of highly complex, protective secondary metabolites. The documented high levels of alpha-tocopherol, beta-carotene, and non-protein thiols like glutathione, which function as potent internal defenses against the oxidative stress inherent in high-efficiency light capture. This chemical sophistication fundamentally undermines the simplistic metrics of modern agronomy that mistakenly prioritize bulk yield and caloric density over chemical complexity and micronutrient bioavailability. Scientific detractors, often aligned with industries promoting alternative or marine-derived omega-3 sources, frequently attempt to minimize the value of plant-based ALA by citing the low endogenous conversion rate of ALA to the longer-chain eicosapentaenoic acid, EPA, 20:5N3, and docosahexaenoic acid, DHA, 22:6N3, in humans, generally estimated to be below 5%. However, this reductionist critique entirely ignores the comprehensive nutritional matrix contained within the purslane biomass itself. The high concomitant levels of essential cofactors, including magnesium, zinc, and crucial B-complex vitamins, specifically pyridoxine, B6, riboflavin, B2, and niacin, B3, all necessary for the activity of the delta-6 and delta-5 desaturase enzymes required for the elongation and desaturation cascade, suggest that purslane provides an inherently optimized, synergistic delivery system. The efficacy of the whole food matrix in stimulating endogenous synthesis potentially surpasses the isolated efficacy of purified ALA supplements, making the traditional dismissal a classic example of reductionist bias overshadowing holistic biological reality. The evidence suggests that the presence of these cofactors potentially elevates the effective conversion efficiency in vivo far beyond theoretical isolated rates, confirming purslane's sustained role as a profoundly complex and resilient nutritional resource designed by evolution, not by industrial patent. This biochemical complexity extends far beyond the well-documented fatty acid and vitamin profiles, encompassing a suite of specialized nitrogenous pigments unique to the order Caryophyllales, the betalains. Unlike the ubiquitous anthocyanin pigments found in standard fruits and vegetables, purslane synthesizes and accumulates betacyanins, responsible for the deep red pigmentation of the stem and leaves, and beta-xanthins, providing yellow hues. These molecules, specifically the beta-cyanin known as portulacaxanthine, exhibit distinct pharmacological properties often overlooked in comparative nutritional analyses. Studies have demonstrated that these compounds possess potent, dose-dependent inhibitory effects on acetylcholinesterase and butyrylcholinesterase activity, suggesting a neuroprotective capacity relevant to mitigating cholinergic deficits observed in neurodegenerative pathologies. This mechanism suggests porcelain may function not merely as a micronutrient delivery system, but as a cognitive modulator, challenging the paradigm that assigns this function primarily to engineered pharmaceuticals or exotic, expensive superfoods. This functional distinction highlights a fundamental evolutionary divergence. While modern agriculture selected for rapid, bland carbohydrate accrual, porcelain evolved intricate defense systems that happen to translate directly into human therapeutic benefit. The critical difference lies in the metabolic origin and functional stability of these specialized compounds. Betalains, being nitrogenous indole derivatives, exhibit exceptional stability across a broader pH range and against thermal processing compared to the pH-sensitive anthocyanins. This stability is critical for maximal bioavailability and efficacy post-ingestion, contrasting sharply with the inherent lability of key micronutrients in many conventionally prepared foods. Furthermore, the robust presence of secondary metabolites like the isoquinoline alkaloids, particularly the oleracein series, A through E, adds another significant layer of pharmaceutical relevance. Research indicates that oleracein E, in particular, mediates potent anti-inflammatory effects by inhibiting the nuclear factor kappa light chain enhancer of activated B cells, or NF-kappa B, signaling cascade, and subsequent inflammatory cytokine release in macrophages. This modulation of critical intracellular signaling pathways suggests a precise mechanism by which porcelain exerts systemic anti-inflammatory benefits that directly address the chronic, low-grade metabolic drivers of modern disease states. The convergence of high omega-3 ELA, superior antioxidant loading derived from synergistic carotenoids, and stable ascorbate, and these neuromodulatory and anti-inflammatory alkaloids places porcelain not just in the category of a nutrient-dense vegetable, but squarely in the highly specialized domain of functional phytomedicine. The systematic devaluation of this resilient organism by modern food science, which often lacks the complex methodologies required to assess such comprehensive, multi-targeted efficacy, constitutes a profound and costly oversight, a direct consequence of prioritizing reductionist metrics based solely on caloric density and yield over ecological and evolutionary insight. The sustained refusal to integrate this data suggests that further exploration into porcelain's role in epigenetic modulation, potentially facilitated by its unique methylation donors and polyamines like spermidine, remains a critical frontier deliberately blocked by the inherent profitability structure of patented synthetic alternatives.